Magnetism. It's that invisible force that sticks a magnet to your fridge, that tells the compass which way is north, and that, believe it or not, powers the very screen you're looking at right now. It is literally everywhere, but it's still one of the most mysterious forces out there. So today, we're going to pull back the curtain and try to make this invisible force, well, a little more visible.
It really does all start with a simple question, right? We use these things every single day, but what is actually going on inside that little souvenir magnet that makes it cling to metal? What is that weird unseen pull? That's the mystery we're going to unravel.
Okay, so first things first. To really get a handle on this, we need a solid definition. What exactly is this force that we can feel but we can't see?
At its heart, it's pretty simple. A magnet is just a material that has the power to attract specific metals. Now, the big three are iron, nickel, and cobalt. If something can pull those metals toward it, then congratulations, you've got yourself a magnet. Yeah, it's basically that straightforward.
Now, here's the thing. While magnetism might feel like magic, it's not random at all. This invisible force follows a really strict and predictable set of rules. You can think of it as the physics of attraction, and it all boils down to three core ideas.
So here's what you need to know. Every magnet has these three key properties. First, it's attractive, and that pull is always strongest at its ends, which we call the poles. Second, it's directive. This is cool. If you just let a magnet dangle freely, it'll always point itself along the Earth's north-south line. That's exactly how a compass works. And third, its goals are inseparable. You can't have a north without a south. If you snap a magnet in half, you don't get a north piece and a south piece. Nope, you get two brand new, smaller magnets, each with its own north and south pole.
And that brings us to the most famous rule of all. Opposites attract. A north pole and a south pole, they'll pull right together. But two of the same kind, two norths or two souths, they'll push each other away. You've probably felt this yourself, right? When you try to force two magnets together the wrong way and you feel that weird spongy resistance, that's a fundamental law of nature pushing back. All right, we've got the basics down, but this is where the story takes a huge, fascinating turn. For centuries, people thought magnetism and electricity were two totally separate things. And then one discovery connected them forever and, I am not exaggerating, completely changed the world. The discovery that changed everything was actually pretty simple. A scientist named Ørsted was doing an experiment and noticed that whenever he switched on an electric current in a wire, the needle of a compass sitting nearby would just twitch. And the conclusion was absolutely revolutionary. Electricity in motion creates its own magnetic field. All of a sudden, these two forces weren't separate at all. They were two sides of the same incredible coin.
And this discovery gives us an incredible power. We can make magnets that we can turn on and off whenever we want. You can literally do this yourself. Just wrap some insulated wire around an iron nail, hook it up to a battery, and boom. As long as that current is flowing, that nail is a magnet. Cut the power, and it goes right back to being just a plain old nail. That's an electromagnet.
And this really shows you the crucial difference. A permanent magnet, like the one on your fridge, is just always on. Its poles are fixed, its strength is what it is. But with an electromagnet, we are in complete control. We can turn it on and off, we can flip its poles just by reversing the current, and we can make it stronger or weaker. And that level of control is the secret ingredient to almost all modern technology, from giant MRI machines to those super-fast maglev trains.
So if we can create a magnetic field with electricity, what can we actually do with that? Well, it turns out this connection is a two-way street. We can use it to turn electricity into motion, and, maybe even more amazing, we can turn motion back into electricity. The first big application is the electric motor. The idea is this. If you put a wire that's carrying an electric current inside a magnetic field, the two fields basically push on each other, and that push creates motion. And there's a super handy trick to figure out exactly which way it's going to move.
Okay, get your left hand ready. No, seriously, try this with me. Point your first finger, your index finger, in the direction of the magnetic field. That's from north to south. Now point your second finger in the direction the electric current is flowing. Your thumb? Well, your thumb is now pointing in the direction of the force. It's showing you which way that wire is going to get pushed. This one simple rule is the basis for every electric motor out there.
But what about going the other way? This is where it gets mind-blowing. The reverse is also true. If you take a wire and you move it through a magnetic field, you will actually generate or induce an electric current in that wire. This is called electromagnetic induction.
And it's how we generate pretty much all the electricity we use on the planet. All right, time to switch hands. For generators, we use the right-hand rule. Point your thumb in the direction you're moving the wire. Point your first finger in the direction of the magnetic field, just like before. And now your second finger will show you the direction of the electric current you just created out of thin air. You're turning motion directly into power.
So we've seen how magnetism works in motors and generators, but now let's zoom way out. Because the most important magnet in your entire life isn't on your fridge. It's the actual planet you're standing on.
That's right. Deep down in our planet's core, there's a constant churning of molten iron and nickel, and that creates massive electrical currents. This motion, combined with the Earth's spin, basically turns our entire planet into a colossal electromagnet. This is why a compass needle points north. It's just a tiny magnet aligning itself with our planet's huge magnetic field. And this planetary field does a lot more than just point compasses north. It's our invisible shield. The sun is constantly blasting out a stream of harmful charged particles called the solar wind. Earth's magnetic field acts like a force field, deflecting most of this dangerous radiation away from us, protecting our atmosphere and all life down here on the surface. Without it, life as we know it simply couldn't exist.
So we'll end on that thought. This invisible force isn't just a neat party trick. It's fundamental to everything, from our technology to our actual survival. It really makes you think, what would our world be like if that invisible shield suddenly flickered and went out?